Hello everyone. In this project, we focus on improving the area and resource utilization of a hardware design using Vitis high-level synthesis. The design implements a discrete cosine transform DCT on an 8 by 8 block of input data, which is commonly used in image and video compression techniques. The implementation is written in C language, and uses a two-dimensional DCT algorithm where the rows of the input matrix are first processed using a 1D DCT, followed by processing the columns of the resulting matrix using the same 1D DCT. The main goal of this project is to enhance performance and optimize the hardware resources by applying HLS optimization techniques such as pipeline, data flow, and memory partition directives. Example, array partition. Uh, these techniques helps reduce latency, improve parallelism, and achieve better resource utilization in FPGA implementation. These uh, these three methods will be very clear when I show you the simulation of these three methods in the Vitis HLS tool. So let me start the simulation. So let me start the video with the initial setup and simulation. The lab begins by running the DCT design through a C language simulation using a TCL script, which is included in the solution one. So let us run the solution one for designing the DCT design using the TCL script. So for running the solution, we should go to the solution tab and run resynthesis, and we have to select the solution as I'm having the multiple solutions here, solution 1, 2, 3. So I have to select solution 1 here and add it. And as you can see that the simulation may take some time. Finally, the output is here. Uh, as we can see, the latency of the solution 1 is very high as the number of cycles present in the latency are 423. And if we compare the absolute latency, it is 4.2230 microseconds. And when we compare the interval cycles, they are 424. And if we go to the memory utilization factors, it uses 17 from 280 available BRAM slots, and it uses 16 from 220 available DSP slots. Like this, there are flip-flops of 1,06,400. It uses only 929. Here the utilization percentage is 6% for DRAM and 7% for DSP, and it is approximately 0 for flip-flops, and it uses 2012 LUTs from 53,200 available slots of LUTs, and the utilization factor is 3. As the utilization factor percentage are very less in the solution 1, uh, so we have to increase the memory bandwidth by using the array partition, which is involved in the solution 2. So the solution 2 involves memory bandwidth improvement using the array partition. The memory size and bandwidth are increased by applying the array partition to key input buffers. This partitioning splits the arrays into smaller parallel segments, reducing memory bottlenecks and enabling parallel data access. So let me run the solution 2 for you. And after running the solution 2, I will compare the solutions of compare the latency and the utilization factors of solution 1 and solution 2, so that we can know it very clearly which solution uses the memory in a better manner and which solution runs in a faster manner. So here's the output of the solution 2. It is this output is called a synthesis details report for DCTs using the array partitioning method. So let me compare the reports of solution 1 and solution 2. For comparing the reports, we have to go to project and we have to go to bottom. There will be an option called compare reports, and we have to select which solution reports we are going to compare. I'm going to compare the reports of solution 1 and solution 2, and this should be added to selected solution, and then OK. So this is the comparison of solution 1 and solution 2. As we can see, the number of cycles present in the latency are 423 in solution 1 and 361 in solution 2. The 423 is greater than compared to 361. So the latency was reduced, and interval cycles are also reduced from 424 to 362. And here the BRAM uses decreases from 17 to 3 BRAM blocks. LUT usage increases due to additional logic from partitioning but remains within the device capacity. This step optimizes the memory usage by replacing large monolithic buffers with partition arrays, enabling parallelism. As we can see here from the utilization estimates, the utilization percentage of DSP was increased as we partitioned the arrays into two parts. The memory usage will automatically increase so that so here it is using 96 blocks of DSP from the 220 blocks availability. So the percentage becomes 43%. In this way, it also enhances the parallelism of the processes. So here we have to enhance this array partitioning method into more effective manner by using the data flow blocks, which is included in solution 3. The third solution applies data flow directives to enable pipeline execution of different parts of the design. So let me run the data flow design also. And after running the solution 3 also, I will compare these three solutions at once. So we can get the clear report of all the three methods. Let's speak of solution 3 was also completed. And let me compare these three solutions together. Compare reports. Solution 1, 2, 3, and okay. This is the comparison report of three solutions. We can see the latency of solution 2 and solution 3 are quite equal. Like it is 361 and 358. Those are very close to each other. But when the interval cycles are compared with solution 1 and solution 2 and solution 3, the interval cycles are reduced drastically from 424 to 224 when compared to the solution 1 and solution 3. Data flow reduces the interval cycles. Interval cycles are the minimum number of cycles between two consecutive operations. The interval cycles are reduced from 424 to 224. This reduction improves the throughput without significantly changing the latency. Uh, this approach decreases the number of loops also. When we see the solution 2, it has 1, 2, 3, 4, 5, 6 loops here. These 6 loops are reduced to 4 loops than in solution 3 by using the pipelining and overlaps data processing stages, thus accelerating the execution. And when compared to the resource utilization, the resource usage also slightly increases in LUTs but remains acceptable for the target FPGA. As we can see, the synthesis details for solution 3. Uh, Here, the resource utilization stays the same for both solution 2 and solution 3, but the latency was quite improved. So let me summarize all the improvements by using these three methods. First one, by using the array partition method. This method primarily improves memory usage and bandwidth by enabling parallel access to input arrays. And the second method, data flow pipelining, it significantly improves performance by reducing interval cycles, and it also enhances the throughput. So as we can see that in the comparison reports of three methods, the latency remains approximately stable across all the solutions. Like it was 420 in the first solution, and it is 360, and in the third solution also it is 358. Uh, the latency was quite similar for the three solutions. The combined optimization may lead to a more resource efficient and higher performance DCT device. So the summarization includes that we should combine these two solutions, like solution 2 and solution 3, for more efficient method, and that efficient method will reduce the latency, and it also enhances the throughput by reducing interval cycles and by reducing latency. Thank you.